Hello there, and welcome. Tonight I want to take you somewhere beyond the everyday noise and routine, somewhere that exists in the quiet spaces between the stars, where mysteries wait patiently for curious minds like yours to contemplate them. I'm so glad you're here, settling into this moment with me, wherever you might be in this vast world of ours. The world is divided into countless time zones, countless rooms where people are seeking the same thing you are right now, a chance to explore, to wonder, and perhaps to find some peace in understanding something greater than ourselves. Before we journey together into the depths of cosmic mystery, I want to know about you. If you're enjoying this cosmic exploration with me, please take a moment to like this documentary, and if you love these kinds of journeys through space and wonder, subscribe so you don't miss where we venture next. I'm curious, where are you watching from right now? What time is it where you are? Is it late evening, deep in the night, or perhaps early morning? Let me know in the comments below. Tell me what part of the world you're calling home as you join me on this expedition into the unknown. Your presence here, wherever you are, makes this a shared exploration, and that matters. Now, let me ask you something that might seem simple on the surface, but carries within it a profound mystery that has occupied the greatest minds of our time. What if everything we see when we look up at the night sky, every distant galaxy, every cluster of stars, every cosmic structure, was being pushed apart by something we cannot see, something we cannot touch, something that seems to defy every law of physics we thought we understood? It's a question that might sound like science fiction, like something from the imagination of a creative mind spinning tales in the darkness. But I assure you, this is grounded in the most careful observations of our universe that science has ever made. And yet, this invisible force, this mysterious power, remains one of the deepest enigmas of our time. You see, we live in an age where we have sent machines to the edges of our solar system, where we have peered deeper into space than ever before, where we have detected the echoes of the Big Bang itself reverberating through the cosmos. And in all of this incredible progress, we have discovered something that should make us pause, something that should fill us with a sense of humble wonder. We have discovered that the universe is not behaving the way we expected it to behave. For centuries, humanity looked up at the stars and saw stability, patterns, order. The ancient astronomers mapped the heavens as if they were fixed and eternal, unchanging in their arrangements. Later, as our understanding grew more sophisticated, we realized the universe was expanding, that galaxies were moving away from each other in an orderly fashion, following the predictions of Einstein's greatest work. But then, in the closing years of the 20th century, something unexpected happened. Scientists observing distant supernovae, these brilliant, momentary deaths of stars that shine with the light of billions of suns, began to notice something peculiar. These distant explosions weren't behaving quite as predicted. They seemed fainter than they should have been, which could only mean one thing. They were farther away than the current models of the universe suggested they should be. This observation, this small deviation from expectation, opened a door to one of the greatest mysteries in cosmology. And it's this mystery, this profound puzzle about the nature of reality itself, that we're going to explore together tonight as we drift deeper into contemplation and wonder. The story of how we came to understand our expanding universe is itself a journey worth taking, a journey that helps us appreciate just how remarkable our current understanding truly is. Imagine, if you will, the perspective of ancient astronomers looking up at the night sky with naked eyes, seeing the stars as eternal and unchanging, arranged in patterns they could map and memorize. They believed the Earth was at the center of everything, that the universe revolved around us. This wasn't foolishness. It was the natural conclusion of careful observation with the tools available to them. Then came the slow revolution of understanding, the gradual realization that we were not at the center, that the sun held a more prominent position, that the stars were impossibly distant suns of their own. But even as telescopes improved and our understanding deepened, the universe itself remained, in the minds of most scientists, a relatively static thing. The Milky Way was thought to be the entire universe, containing all the stars that existed. Everything beyond was thought to be empty void. Then came a pivotal moment in the 1920s, when a young astronomer named Edwin Hubble made observations that would forever change our understanding of reality. Using the most powerful telescope of his time, Hubble observed that there were other galaxies beyond our own, island universes separated from us by incomprehensible distances. But more than that, he made an even more startling discovery. When he examined the light from these distant galaxies, he found that they were moving away from us. The farther away a galaxy was, the faster it seemed to be receding. This was the discovery of cosmic expansion, and it fundamentally altered our understanding of the universe. The universe, it turned out, was not static. It was dynamic, evolving, changing. Space itself was stretching, carrying galaxies along with it like tiny passengers on an expanding ocean. This discovery led to the development of the Big Bang theory, the idea that the universe had begun in an incredibly hot, dense state and had been expanding ever since. The universe, we came to understand, was not infinite in time. It had a beginning, and that beginning was an event of almost incomprehensible violence and energy. As space expanded, it cooled, and particles began to form, then atoms, then the first stars, and eventually galaxies, the vast cosmic structures that populate the universe we observe today. This theory, built on careful observation and mathematical elegance, became the foundation of modern cosmology, and for decades it seemed like we had finally understood the broad strokes of the cosmic story. But the universe, it seemed, had other surprises in store for us. If you're still here with me, contemplating these vast ideas about the nature of space and time, I want to know what you're finding most interesting so far. Are you drawn to the history of discovery? Are you fascinated by how our understanding has changed over time? Please comment below and let me know what's capturing your attention as we journey through these cosmic mysteries together. Your thoughts matter, and I'd love to hear what's resonating with you as we explore these profound questions about our universe. Now, in the quiet depths of space, far from the noise and confusion of everyday life, scientists in the late 20th century began to notice something extraordinary. They were studying the light from distant supernovae, these brilliant cosmic explosions that occur when massive stars reach the end of their lives. Type Ia supernovae in particular are especially useful to astronomers because they all tend to have similar brightnesses when they explode. This means that if astronomers observe a type A supernova in the distance, they can calculate how far away it is based on how bright it appears from Earth. It's like knowing the wattage of a light bulb and then determining how far away it is based on how bright it appears to your eyes. By using this technique, astronomers can map the structure of the universe and understand how rapidly it is expanding at different distances and different times in the past. In 1998, two teams of astronomers, led independently by Saul Perlmutter and Brian Schmidt, made observations that would shake the foundations of cosmology. They had been carefully measuring the distances and velocities of distant supernovae, mapping out how the universe had expanded throughout its history. What they expected to find was that the expansion of the universe was slowing down due to the gravitational attraction of all the matter in the cosmos. After all, gravity pulls things together. The more matter there is, the stronger the gravitational attraction, and the more the expansion should slow. This was the consensus view among cosmologists. The universe would expand, but like a ball thrown upward against Earth's gravity, it would eventually slow down. Some scientists even entertained the possibility that the expansion might eventually reverse, leading to a contraction and eventual collapse, a scenario called the Big Crunch. But the data didn't support this expectation. Instead, the observation suggested something far more surprising. The universe's expansion wasn't slowing down, it was speeding up. Distant supernovae appeared to be farther away than they should have been if the expansion were decelerating, which meant the expansion must be accelerating. In other words, the universe was flying apart faster and faster, driven by some mysterious force that acted opposite to gravity. This was a revolutionary discovery, one that challenged everything scientists thought they understood about the fundamental nature of the cosmos. The observations were painstaking, the data was carefully analyzed, and the conclusions were inescapable. The universe, it seemed, was not just expanding. It was accelerating in its expansion, pushed outward by some invisible force that scientists came to call dark energy. This discovery was so significant that Perlmutter and Schmidt, along with Adam Riess, were awarded the Nobel Prize in Physics in 2011, a recognition of how profoundly their work had altered our understanding of reality. But the prize itself, while an honor, could not answer the fundamental question that their discovery had raised. What was this dark energy? What was pushing the universe apart with ever-increasing force? In many ways, the discovery raised more questions than it answered, and those questions are still being explored and contemplated by physicists and cosmologists around the world today. The mystery deepens as we delve further, and it is this mystery that will guide us through the remainder of our journey together tonight. The implications of this discovery were staggering. If the universe's expansion was indeed accelerating, then the future of the cosmos looked very different from what scientists had previously imagined. Galaxies that were already receding from us would continue to move away, farther and farther into the darkness, until eventually, from our cosmic vantage point, they would disappear from view entirely. The light from distant galaxies would become so redshifted, stretched to such long wavelengths, that we would no longer be able to detect them. Over inconceivably long timescales, trillions upon trillions of years, the universe would evolve into a state where each galaxy was isolated, surrounded by expanding darkness, unable to see any other galaxy in the entire cosmos. This vision of the universe's future was sobering, yet also strangely beautiful in its profound loneliness, and it all hinged on understanding this mysterious force, this dark energy that was driving the acceleration. The observations that revealed dark energy's existence came not from a single source or a single technique, but from multiple independent lines of evidence. Astronomers using different methods, observing different objects, studying different aspects of the universe, all arrived at the same conclusion. The data from Type Ia supernovae was supplemented by observations of the cosmic microwave background, that ancient light left over from the early universe that bathes all of space in its gentle glow. By carefully analyzing the patterns in this ancient radiation, cosmologists could determine the precise geometry of the universe and understand how different forms of matter and energy contributed to its overall structure and evolution. And these observations, conducted with instruments of incredible precision, also pointed to the existence of dark energy as the dominant form of energy in the universe. In fact, according to these observations, dark energy makes up approximately 68% of all the energy in the universe. That's right. Nearly 7 out of every 10 units of energy in the cosmos is this mysterious, invisible substance that we have yet to fully understand. Think about that for a moment. Everything we can see, every star, every galaxy, every cluster of galaxies, all the ordinary matter that makes up planets, people, and everything we've ever known, accounts for only about 5% of the total energy in the universe. Another 27% is dark matter, another invisible substance that exerts gravitational effects but remains invisible to our most powerful telescopes. And the remaining 68% is dark energy, this force that pushes galaxies apart. In other words, nearly 95% of the universe consists of things we cannot directly see or touch. We live in a cosmos that is dominated by the invisible, shaped by forces we are only beginning to comprehend. This realization, this understanding that our universe is so thoroughly mysterious, so filled with unknowns, fills me with a sense of humble wonder. And I hope it fills you with a similar sense of awe as you contemplate the vastness and strangeness of reality. Consider the possibility that this invisible force, this dark energy, has been shaping the universe since the very beginning. Consider that in the moments after the Big Bang, when the universe was unimaginably hot and dense, dark energy may have played a crucial role in determining how the universe expanded and evolved. Consider that every galaxy that exists, every star that shines, every planet that orbits, every moment of cosmic history has been influenced by this mysterious force. We are, in a very real sense, children of dark energy. The universe we inhabit has been shaped by it, and we ourselves are made of material that has been assembled and arranged by the same physical laws that govern dark energy's behavior. There is something profound about realizing that we are connected to this deep cosmic mystery, that it is woven into the very fabric of our existence. The journey to understanding dark energy has been a humbling one for science. For so long, scientists believed they had a pretty good grasp of the fundamental nature of the universe. We understood gravity, understood how matter and energy interacted according to Einstein's equations. We had built a successful theory of how the universe evolved from the Big Bang to the present day. And then, suddenly, observational evidence revealed that something fundamental was missing from our understanding. There was something we had overlooked, something crucial that had been hidden in plain sight. It reminded scientists, and it should remind us all, that the universe is far more subtle, far more intricate, and far more wonderful than we imagine. Every answer we discover leads to new questions. Every mystery we solve reveals deeper mysteries beneath, and perhaps that's the way it should be. Perhaps the universe is infinite, not just in space and time, but also in complexity and in the depth of wonder it can inspire. If you're still journeying with me through this cosmic landscape, I invite you to share your thoughts in the comments below. What fascinates you most about this discovery? Are you intrigued by the idea of an invisible force reshaping the universe? Do you wonder, as I do, what dark energy might ultimately turn out to be? Tell me in the comments what you've found most interesting as we've begun to explore this mystery together. Your engagement, your curiosity, your willingness to contemplate these profound questions. All of it matters, and I want to hear what sparked your wonder. And please, if you haven't already, like this documentary and subscribe so that you can follow along as we continue to unravel the mysteries of the cosmos in the chapters to come. As we continue our exploration, we must venture deeper into understanding what dark energy actually is, or at least what scientists currently theorize it might be. The discovery that the universe's expansion was accelerating raised an immediate and obvious question. What causes this acceleration? What is the mechanism behind it? What is the nature of the force or field that pushes matter apart on cosmic scales? These are not easy questions to answer, because dark energy does not behave like any form of matter or energy we have encountered in our everyday experience or in our laboratory experiments. It is not something we can hold in our hands, examine under a microscope, or detect with a simple instrument. It is revealed only through its effects on the large-scale structure and evolution of the universe. And those effects, while clear and measurable, are also deeply mysterious. One possibility that physicists have seriously considered is that dark energy is related to Einstein's cosmological constant, a term that Einstein himself introduced into his equations more than a century ago. Einstein's original motivation for introducing the cosmological constant was to prevent his equations from predicting that the universe should either be expanding or contracting. At the time, it was thought that the universe was static and unchanging, and Einstein wanted his equations to reflect this belief. However, when Hubble discovered that the universe was actually expanding, Einstein famously called the cosmological constant his greatest blunder and discarded it. But perhaps, just perhaps, Einstein had been onto something all along. Perhaps the cosmological constant was real, perhaps it had been lurking in the universe all along, and perhaps it was the explanation for dark energy and the universe's accelerating expansion. The cosmological constant in modern physics is often interpreted as the energy density of the vacuum itself, the energy that permeates all of space even in the complete absence of any matter or particles. This is a strange concept, one that challenges our intuitions about what empty space really means. In quantum mechanics, the field of physics that governs the behavior of subatomic particles, empty space is not truly empty. It is filled with quantum fluctuations, temporary particles and antiparticles that pop in and out of existence on incredibly short timescales. These quantum fluctuations carry energy, and this energy density is what might constitute the cosmological constant and dark energy. In this interpretation, dark energy is not a mysterious new type of matter or force, but rather a fundamental property of space-time itself. It is the energy of the vacuum, and as space expands, this energy density appears to act as a repulsive force, pushing galaxies apart. However, there is a profound puzzle here, one that physicists have struggled with for decades. When physicists calculate what the vacuum energy density should be based on quantum mechanics, they get a number that is vastly, incomprehensibly larger than what the cosmological observations suggest it should be. This discrepancy, known as the cosmological constant problem, is one of the greatest unsolved mysteries in physics. And yet, despite this puzzle, despite the fact that we don't fully understand what dark energy is, the evidence for its existence is overwhelming. Multiple independent observations all point to the same conclusion. The universe is accelerating in its expansion, driven by something that we call dark energy. As we contemplate this mystery, we must recognize that science is not about having all the answers. Science is about careful observation, about asking questions, about being willing to revise our understanding in light of new evidence. And in the case of dark energy, science has led us to a profound mystery that continues to motivate research and speculation among the world's best physicists. In the silence between the stars, in the vast spaces where galaxies float like islands in an infinite ocean, dark energy works its subtle magic, reshaping the universe moment by moment, driving galaxies farther apart, stretching space itself, creating a cosmos that is ever more vast and ever more lonely. The human mind, when confronted with such mysteries, naturally seeks patterns, seeks explanations, seeks a way to fit the new information into existing frameworks of understanding. And while we have not yet found a complete and satisfying explanation for dark energy, we have made significant progress in understanding how it behaves, what its properties might be, and how it influences the universe on the larger scales. This understanding has come through the careful work of thousands of scientists over decades, using increasingly sophisticated instruments and techniques to observe the cosmos and test hypotheses about its nature. It is a testament to human curiosity, human ingenuity, and the power of the scientific method that we have come as far as we have in understanding something so fundamentally mysterious. Now let us turn our attention to something even more extraordinary. Let us consider what it means for dark energy to push galaxies to speeds that exceed the speed of light. This might seem to violate one of the most fundamental principles of physics, the principle that nothing can move faster than light. But here is where we must be careful with our language and our understanding. When we say that galaxies are moving faster than light, we do not mean that they are moving through space faster than light. Instead, we mean that space itself is expanding so rapidly that the distance between us and distant galaxies is increasing at a rate greater than the speed of light. This is an important distinction, and it reveals something profound about the nature of space and time in our universe. In Einstein's theory of relativity, nothing can move faster than light through space, but space itself, the very fabric of the cosmos, can expand at any rate whatsoever. There is no cosmic speed limit on the expansion of space itself, so when we observe that distant galaxies are receding from us at speeds greater than the speed of light, we are not observing anything that contradicts relativity. We are simply observing the expansion of space on cosmic scales. The galaxies themselves are not moving through space at these tremendous speeds. Rather, space is expanding between us and them, carrying them away from us at accelerating rates. This distinction might seem subtle, but it is crucial to understanding how the universe can behave in ways that might initially seem to violate physical laws that we hold dear. Imagine a balloon with dots painted on its surface. Now imagine that the balloon is inflating, expanding in all directions. The dots represent galaxies, and they are painted on the surface of the balloon, representing the three-dimensional space of our universe. As the balloon inflates, the dots move apart from each other. From the perspective of any single dot, all other dots appear to be moving away. The farther away a dot is, the faster it appears to be moving away, simply because there is more balloon surface between them as it expands. And if the balloon inflates fast enough, the rate at which distant dots move apart can exceed the speed of light, or any other speed for that matter. Yet none of the dots are moving through the rubber of the balloon faster than light. They are simply being carried apart by the expansion of the balloon itself. This is precisely what is happening in our universe. Galaxies are not racing through space at faster than light speeds. Instead, space itself is expanding, carrying them apart at accelerating rates. The concept of superluminal recession, as astronomers have come to call it, raises fascinating questions about the nature of distance and separation in an expanding universe. When we observe a galaxy that is receding from us at speeds greater than the speed of light, we are looking at something that challenges our most basic intuitions about space and motion. Yet this phenomenon is not only possible within the framework of relativity, it is inevitable in a universe that is expanding rapidly enough. As space stretches between us and these distant galaxies, they slip beyond what is called the cosmic horizon, the boundary beyond which we can never receive light or information from them, no matter how long we wait. This is not because they are moving away so fast that their light cannot catch up with the expansion, though in a sense that is what is happening, but rather because the very space through which their light would have to travel is expanding faster than the light can traverse it. Imagine trying to walk toward a distant doorway, but but the ground between you and the doorway is stretching faster than you can walk. No matter how quickly you move forward, you never get any closer to the doorway. In fact, you might actually be moving farther away. This is the situation facing light from distant galaxies in an acceleratingly expanding universe. The light begins its journey toward us with the intent of revealing to us the distant galaxy from which it originated. But as it travels through expanding space, that space is stretching so rapidly that the light never actually makes progress toward us. Instead, it is carried backward, away from us, by the expansion of space itself. This is a humbling realization. It means that there are galaxies in the universe whose light will never reach us, no matter how far into the future we wait. There are structures, events, and phenomena happening in the cosmos that are forever hidden from our view, not because they are obscured by dust or darkness, but simply because they exist beyond the cosmic horizon, in a region of space that is expanding away from us faster than light can travel. The implications of this are profound and thought-provoking. If we could somehow peer into the future, billions upon billions of years from now, we would see a universe that looks very different from the one we observe today. In the far distant future, most galaxies will have receded beyond the cosmic horizon. From our vantage point in the Milky Way, we would see only our own galaxy, and perhaps a few nearby companions that have remained gravitationally bound to us. The rest of the universe would be invisible, hidden not by distance alone, but by the expansion of space itself. Future astronomers studying the sky from our galaxy in this remote future epoch would look up at the night sky and see very little. They would not know, without access to our historical records, that there were ever other galaxies in the universe at all. They would live in a cosmos that appeared to all observations to contain only their own galaxy. This is a fate that awaits the universe in the incomprehensibly distant future, assuming that dark energy continues to drive the expansion at accelerating rates. But we, fortunate beings that we are, live in a cosmic epoch where we can still see distant galaxies, where the universe still reveals itself to us through the light that travels across billions of light years to reach our eyes and our telescopes. We live in a golden age of astronomy, a time when our universe is still transparent to our observations, when we can still peer deep into space and time and witness the cosmos as it was billions of years ago. This is a remarkable privilege, and it is one that will not last forever. Future generations in the far future will not have this advantage. They will live in a universe that has become increasingly opaque, increasingly isolated, with fewer and fewer galaxies visible in the night sky. This realization should fill us with a sense of gratitude for the time in which we live, and a sense of urgency to understand the cosmos while we still can. The universe is revealing its secrets to us now, and we should cherish this opportunity. The observation that galaxies beyond certain distances are receding faster than the speed of light has profound implications for cosmology and our understanding of time itself. It tells us that the universe has a structure that is fundamentally different from what we might have naively expected. The universe is not just a collection of matter scattered through empty space. Rather, space itself is a dynamic, evolving entity, subject to forces and influences that we are only beginning to comprehend. The expansion of space is not something that happens to the universe. It is something that the universe does, a fundamental aspect of its nature and evolution. And dark energy, this mysterious force that drives the acceleration of expansion, is intimately connected to the very nature of space-time itself. The redshift observations that revealed the acceleration of expansion provide us with a window into understanding how dark energy behaves across cosmic time and distance. When astronomers observe a distant galaxy, they measure the wavelengths of light coming from it. If a galaxy is moving away from us, the light is stretched to longer wavelengths, a phenomenon called redshift. The faster the galaxy is moving away, the greater the redshift. By carefully measuring redshifts and comparing them with the apparent brightnesses of supernovae, astronomers can determine not just the current rate of expansion, but how the expansion rate has changed over the history of the universe. These observations reveal that the expansion was decelerating in the early universe, driven by gravity pulling matter together. But at some point, roughly 5 to 6 billion years ago, the expansion began to accelerate. This transition point, this moment when dark energy's influence began to dominate over gravity, marks a crucial turning point in cosmic history. What happened 5 to 6 billion years ago was not some cosmic cataclysm or sudden event. Rather, it was a gradual shift in the balance between the forces that govern cosmic evolution. As the universe expanded, it became less dense. Gravity, which depends on density, became weaker. Meanwhile, dark energy, which appears to maintain a constant energy density even as space expands, became relatively more important. Eventually, dark energy's repulsive influence overwhelmed gravity's attractive influence, and the expansion began to accelerate. This transition is written into the structure of the universe itself, recorded in the distances and velocities of galaxies, and in the patterns of the cosmic microwave background radiation. By studying these observations, cosmologists can reconstruct the history of cosmic expansion and understand how dark energy has influenced the universe throughout its history. The Hubble Space Telescope and other modern observatories have been instrumental in making the precise measurements that revealed dark energy and the cosmic acceleration. These incredible instruments, positioned above Earth's atmosphere or operating from the ground, with advanced techniques to correct for atmospheric distortion, have allowed astronomers to observe supernovae and galaxies at distances and with clarity that would have been impossible just decades ago. The Hubble Space Telescope, named after Edwin Hubble, the astronomer whose discoveries revealed the expansion of the universe, has observed thousands of supernovae and measured their distances with unprecedented precision. The data from these observations, accumulated over years of careful work, has provided the evidence that dark energy not only exists, but dominates the dynamics of the universe on the largest scales. But the story does not end with the discovery of cosmic acceleration. Instead, this discovery opened new avenues of investigation and raised new questions that scientists are still working to answer. If dark energy is real, and if it is driving the acceleration of expansion, then we must ask, what is it? How does it work? Will its effects remain constant in the future, or might dark energy's influence change over time? These are not just abstract philosophical questions. They have practical implications for understanding the fate of the universe and for testing our most fundamental theories of physics. Dark energy challenges us to expand our conceptual frameworks, to think more deeply about the nature of reality, and to remain humble in the face of cosmic mysteries that we do not yet fully understand. Perhaps what makes dark energy so fascinating is not just that it is mysterious, but that it reveals the limits of our current knowledge while simultaneously pointing toward new frontiers of discovery. We know that dark energy exists. We know that it is pushing galaxies apart. We know that it dominates the universe energetically. But we do not know what it is, not with complete certainty. We do not have a complete and satisfying explanation that emerges naturally from our fundamental theories of physics. And this gap between observation and understanding is precisely where science thrives. It is in these gaps, in these spaces between what we know and what we do not yet understand, that the most exciting discoveries are waiting to be made. And it is in contemplating these mysteries that we exercise our greatest faculty, the ability to wonder, to question, to seek understanding of the world around us. As we venture deeper into the cosmos, we must consider not just what dark energy is doing now, but what it may have done in the past and what it might do in the future. In the very early universe, in the first fractions of a second after the Big Bang, the universe was infinitely hot and dense. The conditions were so extreme that our current understanding of physics breaks down. We cannot, with our current theories, describe what happened at the very moment of the Big Bang itself, but we can describe what happened in the first microseconds and seconds after it. And in those earliest moments before normal matter had even formed, dark energy may have played a crucial role in determining the structure and fate of the universe. Some cosmologists have speculated that dark energy, or something very much like it, may have driven a period of exponential expansion in the very early universe, an epoch called inflation. This inflationary period would have stretched quantum fluctuations to cosmic scales, creating the seed structures that would eventually grow into galaxies and galaxy clusters. In this view, dark energy, or its precursor, has been shaping the universe since the very beginning, and everything we observe today, every star, every planet, every person, owes its existence to dark energy's influence. The question of dark energy's constancy is particularly intriguing. Does dark energy's density remain constant as the universe expands, or does it change over time? The observations so far suggest that it remains constant, or nearly so, which is consistent with the cosmological constant interpretation. But some theories propose that dark energy might be dynamic, that its density might vary with time. If dark energy's properties were to change in the future, the fate of the universe might be different from what we currently predict. Perhaps the expansion might slow down again at some point in the far future. Perhaps dark energy's repulsive influence might intensify, leading to scenarios where eventually even atoms themselves would be torn apart by the expansion. This hypothetical scenario, sometimes called the Big Rip, is a sobering thought, though there is no observational evidence that it will actually occur. More likely, based on current observations, the universe will continue to expand at an accelerating rate indefinitely, becoming increasingly empty, increasingly dark, increasingly lonely. The distances involved in cosmic expansion are almost impossible for the human mind to grasp. When we say that a galaxy is receding at a certain speed, we're talking about speeds that dwarf any velocity we experience in our everyday lives. The fastest spacecraft humanity has ever built travels at speeds of tens of kilometers per second, impressive by terrestrial standards but utterly trivial compared to cosmic speeds. A distant galaxy might be receding at speeds of tens of thousands of kilometers per second, or even faster. And as we look to galaxies that are even more distant, we find recession velocities approaching the speed of light itself, 300,000 kilometers per second. These are speeds that seem almost abstract, almost incomprehensible, yet they are measured by our telescopes and confirmed by our observations. They tell us that the universe is not just big, it is unimaginably, almost infinitely vast, and it is expanding in ways that challenge our deepest intuitions about space and motion. Consider the possibility that as dark energy pushes galaxies apart, as space expands at accelerating rates, the very structure of the universe is being fundamentally altered. Galaxies that are now neighbors, separated by millions of light years, will eventually become isolated beyond the cosmic horizon. The universe, which began as a hot, dense point containing all of space-time and all of matter and energy, will eventually become a cold, empty expanse where vast regions of space are separated by distances so immense that they can never exchange light or information with each other. This is not a catastrophe in the sense of some violent cataclysm. It is rather a slow, gradual transformation of the cosmos into a state of maximum isolation and entropy. And yet, there is something almost beautiful about it, something that speaks to the sublime nature of cosmic evolution. The universe, in a sense, is slowly fading away into darkness, not all at once but gradually over time, scale so vast that trillions of years pass before the transformation is complete. The human perspective. Our place in this vast cosmic drama is almost impossibly small. We are made of atoms forged in the centers of stars. We inhabit a planet that orbits an ordinary star in an ordinary galaxy. That galaxy, immense though it is, contains hundreds of billions of stars and is itself just one among hundreds of billions of galaxies in the observable universe. The observable universe itself, everything we can possibly see, is just a tiny fraction of what might exist beyond our cosmic horizon, and we, conscious beings capable of contemplating all of this, are even smaller still. Temporary arrangements of matter that persist for but a brief moment in the cosmic timeline, and yet our smallness does not diminish our significance, rather it heightens it. We are among the rarest, most remarkable structures in the universe, conscious observers capable of understanding the cosmos, that we can look up at the night sky and wonder about dark energy, that we can construct theories and perform observations to test those theories, that we can contemplate the grand architecture of the universe and our place within it. This is something genuinely extraordinary. Now, let us consider what lies beyond the cosmic horizon, in the regions of space where no light from Earth will ever reach, where no information can ever travel to us across the expanding void. These regions are not empty or devoid of structure. They almost certainly contain galaxies, stars, and perhaps even planets and life. But they are forever hidden from us, forever separate from us, not by any barrier or obstacle, but simply by the expansion of space itself. This is a humbling realization. It means that the universe we can see, for all its vastness, is just a tiny window into a cosmos that is incomparably larger. It means that our knowledge of the universe, no matter how advanced our technology becomes, will always be incomplete and limited. And it means that there are mysteries in the cosmos that we will never be able to solve, questions that will never be answered because the evidence will always lie beyond our reach. The cosmic horizon itself is not a fixed thing. It is constantly receding as the universe expands and as light from more distant regions has time to reach us. In principle, if we wait long enough, light from regions that are currently beyond our cosmic horizon might eventually reach us. But because the expansion is accelerating, this process becomes increasingly unlikely. Most of the regions beyond our current cosmic horizon will retreat faster and faster away, and the light from them will never reach us. Instead, the cosmic horizon will gradually shrink and recede, until eventually only our own galaxy and a few nearby companions remain visible. This future state of the universe will be profoundly different from the present, yet it is an inevitable consequence of dark energy and the cosmic acceleration, assuming that dark energy's properties remain as they appear to be now. If you have journeyed with me this far into these cosmic mysteries, I want to express my gratitude for your presence and your attention. These are deep and contemplative ideas, and the fact that you are still engaging with them, still wondering about dark energy and cosmic expansion, speaks to the curiosity and intelligence that burns within you. I encourage you to comment below and share what thoughts and feelings have arisen as you have contemplated these cosmic mysteries. What aspects of cosmic expansion intrigue you most? Do you find yourself pondering what lies beyond the cosmic horizon? Are you moved by the realization that vast regions of the universe will forever remain hidden from our view? Tell me in the comments what thoughts are resonating with you as we explore these profound cosmic truths. And if you are finding this documentary enriching, if these ideas are sparking wonder in your mind, please like this video and subscribe so that you can follow along as we continue to explore the deepest mysteries of existence. The observations of distant supernovae have given us more than just evidence of dark energy's existence. They have given us a detailed map of cosmic expansion throughout history. By observing supernovae at various distances, which means observing them as they were at various times in the past, cosmologists can reconstruct how the expansion rate has changed over billions of years. This cosmic expansion history shows clearly the transition from a decelerating expansion, when gravity was dominant, to an accelerating expansion, when dark energy became dominant. It shows how the universe has evolved from a state where it was being pulled together by gravity to a state where it is being pushed apart by dark energy. This evolution is not random or chaotic. It follows clear patterns that are consistent with our understanding of how matter and energy behave under gravity and other fundamental forces. The measurements of redshift and distance that underlie all of this cosmic archaeology are remarkably precise. Modern spectrographs can measure the wavelengths of light from distant objects with accuracy that would have seemed impossible just a few decades ago. A supernova at a distance of billions of light years has its light spread across the optical spectrum, and each element in the supernova, iron, nickel, oxygen, silicon, produces characteristic spectral lines at specific wavelengths. When these lines are shifted toward longer wavelengths due to cosmic expansion, the amount of shift can be measured with extraordinary precision. This measurement allows astronomers to determine not just the distance to the supernova, but the rate at which space was expanding at the time the light was emitted, billions of years in the past. It is a remarkable achievement of observational astronomy, a testament to human ingenuity and the power of careful measurement and analysis. The type of supernova most useful for studying cosmic expansion is the type Ia supernova, which occurs in a binary star system where a white dwarf, the dense remnant of a star like our Sun, is pulling material from a companion star. As the white dwarf accumulates material, its temperature and pressure increase. Eventually, the temperature reaches a critical point, and thermonuclear fusion begins throughout the entire star, not just in a shell on its surface. The entire white dwarf explodes in a runaway thermonuclear reaction, obliterating the star and releasing tremendous amounts of energy. The brightness of a type Ia supernova is determined primarily by how much radioactive material is produced in the explosion, and how much of that material is synthesized into elements that emit light in visible wavelengths. For this reason, type Ia supernovae tend to have roughly similar peak brightnesses, making them excellent standard candles for measuring cosmic distances. But type Ia supernovae are not the only tools that cosmologists use to study dark energy and cosmic expansion. The cosmic microwave background radiation, the the ancient light left over from the early universe, also carries information about dark energy. By carefully analysing the patterns and power spectrum of the cosmic microwave background, the tiny temperature fluctuations imprinted on it from the early universe, cosmologists can determine the geometry of the universe and the relative abundances of different forms of matter and energy. These observations, made with exquisite precision by satellites like WMAP and Planck, have provided independent confirmation of dark energy's existence and have constrained the properties that dark energy must have. When cosmologists combine the supernova data, the cosmic microwave background data, and data from other sources like galaxy clusters and large-scale structure observations, they get a consistent picture. Dark energy makes up about 68% of the universe. Ordinary matter makes up about 5%. Dark matter makes up about 27%. And the universe is expanding at an accelerating rate driven by dark energy's repulsive effects. The fact that multiple independent lines of evidence all point to the same conclusion, that dark energy exists and dominates the universe, gives us high confidence in this conclusion. It is not based on a single observation or a single technique. Rather, it is a robust conclusion that emerges from the careful analysis of many different types of observations made by many different research groups around the world. This is how science works at its best. When multiple independent approaches all converge on the same answer, we can be reasonably confident that we are uncovering a genuine feature of reality, not just an artifact of observation or analysis. Of course, science always remains open to new evidence that might require us to revise or refine our understanding. But the current evidence for dark energy and cosmic acceleration is about as solid as scientific evidence can be. As we contemplate the implications of dark energy and cosmic expansion, we must grapple with some truly mind-bending ideas. We must accept that space itself is expanding, that the very fabric of the cosmos is being stretched, carrying galaxies apart at rates that can exceed the speed of light. We must accept that there are regions of the universe whose light will never reach us, not because of any physical barrier, but because space itself is expanding faster than light can traverse it. We must accept that the universe we can see is just a tiny fraction of what exists, and we must accept that the future of the cosmos, billions upon billions of years from now, will be radically different from the present, with galaxies isolated in the darkness, unable to see any other galaxy in the entire universe. These are not easy ideas to accept. They challenge our intuitions about space, time, and the nature of reality itself, and yet the evidence for them is compelling, and understanding them is essential to understanding the universe we inhabit. The study of dark energy has also led to some profound philosophical questions. If dark energy fills all of space, if it is the dominant form of energy in the universe, then what does that tell us about the fundamental nature of reality? Is dark energy a form of substance, a thing that exists in its own right, or is it simply a manifestation of something deeper, some property of space-time itself that we have not yet understood? Is the vacuum truly empty, or is it filled with structure and energy? These questions touch on some of the deepest issues in physics and philosophy. They cannot be answered by observation alone. They require careful theoretical work, creative thinking, and a willingness to entertain possibilities that might seem strange or unintuitive. The universe, as we have come to understand it through decades of careful observation and theoretical work, is far stranger and more wonderful than our ancestors could have imagined. It contains within it forces and phenomena that defy easy explanation and comfortable understanding. And yet this strangeness, this mystery, this profound not knowing, is not something to be feared or avoided. Rather, it is something to be embraced and celebrated. It is in the face of such mysteries that we grow, that we learn, that we develop our understanding and expand our minds. The universe is inviting us, in a sense, to join in a great cosmic conversation, to ask questions, to seek understanding, to marvel at the complexity and beauty of creation. In the quiet hours of the night, when the world is still and the stars are visible above, it is natural to contemplate these cosmic mysteries. It is natural to look up at the night sky and wonder about what we are seeing, what it all means, and what lies beyond the reach of our telescopes and our knowledge. Dark energy is not something we see directly. It is something we infer from observations, something we understand through its effects on the large-scale structure and evolution of the universe. But perhaps that is fitting. Perhaps the most profound mysteries of the cosmos are those that we cannot see directly, but must understand through careful observation and deep thinking. Perhaps the greatest cosmic secrets are revealed not through the light of distant stars, but through the subtle effects of invisible forces working their way throughout the universe, shaping and reshaping the cosmos in ways that we are only beginning to comprehend. And perhaps in contemplating these mysteries, in allowing ourselves to wonder about dark energy and cosmic expansion, we are touching something deep within ourselves, something that connects us to the grand adventure of cosmic discovery and understanding. In the quiet depths of space, far beyond the reach of our most powerful telescopes, the universe continues its endless dance of expansion, driven by dark energy's invisible hand. But to truly understand this cosmic force, we must look more carefully at the evidence that surrounds us, at the whispers and messages that the universe sends across billions of years of space and time. These whispers come to us in many forms, encoded in light that has traveled for eons, imprinted on radiation that bathes all of space, written into the large-scale structure of galaxies and galaxy clusters. When we learn to listen to these whispers, when we develop the instruments and the understanding to decode their messages, the universe reveals profound truths about its nature and its evolution. The cosmic microwave background radiation, that ancient light left over from the earliest moments of the universe, carries within it the imprint of dark energy's influence. This radiation was released about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and light to travel freely through space. In a sense, it is a photograph of the universe taken at an incredibly early moment in cosmic history, before galaxies had even formed, when the universe was still young and filled with glowing gas. This photograph has been preserved for 13,800,000,000 years, traveling across the cosmos, carrying with it information about the physical conditions and processes that shaped the early universe. The cosmic microwave background appears to us as a faint glow of radiation coming from all directions in space, with a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. If we were to map the temperature of this radiation across the entire sky, we would find that it is not perfectly uniform. There are tiny temperature fluctuations, variations of just a few millionths of a degree, but these tiny variations carry enormous amounts of information. They reveal where regions of slightly higher and slightly lower density existed in the early universe, the seeds of cosmic structure that would eventually grow into galaxies and galaxy clusters. By carefully analyzing the pattern of these temperature fluctuations, cosmologists can determine fundamental properties of the universe, including the total amount of energy and matter it contains and how that energy and matter are distributed among different forms. These analyses have revealed that dark energy makes up about 68% of the universe's total energy content, confirming the conclusions that were drawn from the supernova observations. The agreement between these two independent techniques is remarkable and reassuring. It tells us that we are not fooling ourselves, that dark energy is not some artifact of how we are interpreting supernova data, but rather a genuine feature of the universe that shows up in multiple different ways when we observe and analyze the cosmos. Another powerful technique for studying dark energy is the measurement of baryon acoustic oscillations, subtle patterns in the distribution of galaxies that reflect the acoustic waves that propagated through the early universe before the cosmic microwave background was released. In the early universe, matter and radiation were coupled together in a hot plasma. Sound waves could propagate through this plasma, creating regions of slightly higher and slightly lower density. The acoustic waves had a characteristic wavelength, determined by the interplay of gravity and radiation pressure. When the universe cooled and atoms formed, these density waves became frozen into the structure of matter. The characteristic scale of the acoustic waves, which was about 450 million light-years in the present universe, shows up as a peak in the clustering of galaxies at that particular separation. By measuring this characteristic scale in the distribution of nearby galaxies, astronomers can determine how fast the universe was expanding at different times in the past, which in turn constrains the properties of dark energy. Multiple independent measurements of baryon acoustic oscillations have been made, and they all agree with the conclusions drawn from supernova observations and cosmic microwave background analysis. Dark energy exists, it dominates the universe, and its repulsive effects are causing the expansion to accelerate. The evidence for dark energy is thus not a matter of interpretation or opinion, It is a robust conclusion that emerges from the careful analysis of multiple different types of observations, made using different techniques, different instruments, and different teams of scientists around the world. When such convergence of evidence occurs, when multiple independent approaches all point to the same conclusion, we can be very confident that we have uncovered a genuine feature of reality. And yet, even with all of this evidence, even with our observations pointing clearly to dark energy's existence and dominance, the fundamental question remains unanswered. What is dark energy? What is its true nature? What are its properties? And how does it fit into our deepest theories of physics? These are questions that physicists and cosmologists continue to grapple with, and they are questions that will likely occupy researchers for many years to come. The gravitational lensing of light provides yet another window into understanding the large-scale structure of the universe and the effects of dark energy. When light from a distant galaxy passes near a massive structure, such as a galaxy cluster, the gravity of that structure bends the light's path, magnifying and distorting the image of the distant galaxy. This effect, predicted by Einstein's theory of relativity and observed countless times by astronomers, allows us to map the distribution of matter in the universe, including both ordinary matter and dark matter. By studying how light is bent by massive structures, we can determine the distribution of all forms of matter and energy in the universe. And these observations of gravitational lensing, when combined with other data, again confirm the existence of dark energy and its dominance in the cosmic energy budget. The picture that emerges from all of these different observational techniques is consistent and compelling. We live in a universe dominated by dark energy, a mysterious force that drives cosmic expansion at accelerating rates, carrying galaxies apart and shaping the future of the cosmos in ways we're only beginning to understand. The Planck satellite, launched by the European Space Agency in 2009 and operated until 2013, made observations of the cosmic microwave background with unprecedented precision. The satellite was able to measure the tiny temperature fluctuations in the ancient light, with a resolution and sensitivity that far exceeded previous instruments. The data from Planck allowed cosmologists to determine the properties of the universe with extraordinary accuracy. It confirmed the presence of dark energy and determined that it makes up about 68.3% of the universe's total energy content. The Planck data also revealed that the universe has a flat geometry, meaning that space extends without bound in all directions, and that parallel lines remain parallel, at least on large scales. This flatness is significant because it tells us that the total energy density of the universe is exactly equal to the critical density, the density at which the universe would have just enough gravity to prevent infinite expansion, but not enough to cause recollapse. The fact that the universe is so precisely flat suggests that either we are observing it at a special moment in cosmic history, which would be an incredible coincidence, or that some mechanism, such as inflation in the early universe, drove the universe toward flatness in the distant past. The WMAP satellite, which preceded Planck and operated from 2001 to 2013, also made crucial observations of the cosmic microwave background. The data from WMAP, combined with observations from other sources, provided the first clear evidence that dark energy was driving cosmic acceleration. The scientists working with WMAP data were able to determine that the universe had been decelerating in its expansion for most of its history, but that at some point roughly 5 to 6 billion years ago the expansion began to accelerate. This transition point, this moment when dark energy's influence began to overcome gravity's attraction, represents one of the most important turning points in cosmic history. Before this transition, the universe was expanding more slowly over time due to gravity. After this transition, the universe began expanding faster and faster as dark energy pushed matter apart. We are living in the epoch after this transition, an epoch where dark energy dominates the dynamics of cosmic expansion. The implications of living in a dark energy-dominated universe are profound and far-reaching. The universe we observe today is not the same as the universe of the distant past, nor will it be the same as the universe of the distant future. The universe evolves, changes, develops over time in response to the interplay between gravity, which pulls matter together, and dark energy, which pushes matter apart. Currently, dark energy is winning this cosmic struggle. Its repulsive effects are overwhelming gravity's attractive influence on the larger scales, driving galaxies apart at accelerating rates. But this has not always been the case. In the very early universe, when matter and energy were much more densely packed, gravity was the dominant force. It was gravity that pulled matter together to form the first galaxies and stars. It was gravity that created the structure and complexity that we see in the universe today. Dark energy was always present, always exerting its subtle repulsive effects, but for billions of years it was overshadowed by gravity. Only relatively recently, in cosmic terms, has dark energy become dominant, and only in the future will its full effects become apparent. When we observe distant galaxies and measure their distances and velocities, we are essentially looking back in time. Because light travels at a finite speed, when we observe a galaxy that is billions of light years away, we are seeing it not as it is today, but as it was billions of years ago, when the light was emitted. A galaxy that appears to be 10 billion light years away is being seen as it was 10 billion years ago, at a time when the universe was much younger. By observing galaxies at various distances, which means observing them at various times in the past, we can reconstruct the history of cosmic expansion. We can see how fast the universe was expanding at different times, and from this information, we can infer the properties of dark energy and understand how its influence has changed over cosmic time. The observations show clearly that the expansion has accelerated in recent cosmic history, even as it was decelerating in the more distant past. This acceleration is the signature of dark energy's influence, and it is one of the most significant discoveries in cosmology. The redshift of light from distant galaxies is perhaps the most direct way to observe cosmic expansion. When a galaxy is moving away from us, the wavelengths of light coming from it are stretched, shifted toward longer, redder wavelengths. The amount of this redshift is directly related to how fast the galaxy is moving away, and, more fundamentally, to how much the universe has expanded since the light was emitted. By measuring the redshift of light from distant galaxies, astronomers can determine how far away the galaxies are and how fast space has expanded. By combining redshift measurements with measurements of the apparent brightness of supernovae, astronomers can determine the expansion history of the universe and constrain the properties of dark energy. The relationship between redshift and distance is not linear. At large distances, the relationship becomes more complex, reflecting the changing expansion rate of the universe over time. By carefully measuring this relationship across a range of distances, astronomers can create a detailed map of cosmic expansion history, revealing how dark energy has influenced the universe throughout its past, and providing clues about its nature and future influence. If you're still journeying with me through these cosmic mysteries, if you have followed along as we have explored dark energy and cosmic expansion from multiple angles, I want to acknowledge the effort and attention you have invested in this exploration. These are not simple ideas. They challenge our understanding of space, time, and reality itself. The fact that you are willing to contemplate them, to sit with the mystery and wonder about it, speaks to the depths of curiosity and intelligence within you. I would love to hear your thoughts and reflections on what we have discussed so far. What aspects of dark energy intrigue you most? Have the multiple lines of evidence we have examined, supernovae, cosmic microwave background, baryon acoustic oscillations, gravitational lensing, given you a sense of how well supported the conclusions about dark energy are? What questions remain in your mind about the nature of this mysterious force? Please share your thoughts in the comments below. Tell me what has captured your attention, what has sparked your wonder, what mysteries you are pondering as you contemplate the cosmos. And if you are finding value in this exploration, if these ideas are enriching your understanding and awakening your sense of cosmic wonder, I encourage you to like this video and subscribe so that you can continue this journey with me as we venture deeper into the mysteries of existence. The future evolution of the universe, shaped by dark energy's persistent push, is something that cosmologists have contemplated extensively. If dark energy continues to behave as it currently appears to behave, maintaining a constant energy density even as the universe expands, then we can predict with reasonable confidence what the universe will look like trillions of years from now. The expansion will continue to accelerate. Galaxies will continue to move away from us at ever-increasing speeds. Eventually, billions of years from now, most galaxies will have receded beyond the cosmic horizon, hidden by the expansion of space itself. The universe will become increasingly dark, increasingly empty, increasingly lonely. Stars will age and burn out. The atoms that make up stars and planets will decay. Eventually, after incomprehensibly long timescales, the universe will reach a state of maximum entropy, a state of cold, darkness and emptiness, where nothing remains but radiation and perhaps the lightest elementary particles drifting through an infinite void. This ultimate fate of the universe, sometimes called heat death or the Big Freeze, is a sobering thought, yet it is a logical consequence of dark energy's continued dominance and the second law of thermodynamics, which dictates that the entropy of the universe always increases over time. But perhaps this ultimate fate is so far in the future that it need not concern us. The universe will remain relatively habitable, relatively structured, relatively interesting for many trillions of years to come. Stars will continue to form and burn out. Planets will orbit those stars. Life might arise on some of those planets. Civilizations might emerge and develop, contemplating the cosmos just as we're doing now. And all of this will happen in a universe where dark energy shapes the large-scale structure and destiny. For the foreseeable future, from a human perspective, the universe will continue to be a place of complexity and interest, a cosmos where structure and life are possible. The dark future we have imagined is so remote, so far in the future that it is almost abstract, almost unreal. What matters to us now is understanding the universe as it is, appreciating the remarkable place we occupy in it, and wondering about the forces and mysteries that shape our cosmos. The acceleration of cosmic expansion driven by dark energy has also profound implications for the ultimate fate of large-scale cosmic structures. Over trillions of years, in the very far future, galaxies will become increasingly isolated, separated from each other by expanding voids that grow larger and larger. The groups and clusters of galaxies that are bound together by gravity will eventually become isolated, unable to interact with other structures. Within bound structures like our own Milky Way, stars will eventually be ejected by gravitational interactions with each other, escaping into the intergalactic void. The stellar remnants and planets that remain will slowly cool. The universe will become darker and colder. But again, all of this is so far in the future that it is almost incomprehensible. For the next 100 billion years or more, the universe will continue to be a place where galaxies, stars and planets exist, where complexity and structure persist, where life might arise and civilizations might develop. In the present epoch, in the universe we observe today, dark energy's effects are subtle on small scales. The expansion of space driven by dark energy does not tear apart galaxies or stars or atoms. Gravity remains the dominant force on small scales, holding stars together, holding galaxies together, holding us together. Only on the largest cosmic scales, where gravity becomes weak because of the vast distances involved, does dark energy's repulsive influence overcome gravity's attractive influence. This is why galaxies are moving apart, why the cosmic expansion is accelerating, yet the universe around us seems stable and structured. We do not feel dark energy's push in our daily lives. We do not see it tearing the Earth apart or dispersing the atoms of our bodies. Dark energy is a force that operates on cosmic scales, affecting the universe as a whole, determining the fate of galaxies and galaxy clusters, shaping the large-scale structure of the cosmos. On smaller scales, on the scales that are relevant to planets, stars, and even galaxies, gravity and the other fundamental forces dominate. This division between small-scale and large-scale physics, between the realm where gravity is dominant and the realm where dark energy dominates, is a fundamental feature of our universe. The observation that dark energy seems to have a constant energy density is particularly intriguing. As the universe expands, all forms of matter and radiation become diluted. The density of ordinary matter decreases. The density of radiation decreases. The density of dark matter decreases. But the density of dark energy appears to remain constant. This unusual behavior is one of the mysteries surrounding dark energy. Why does its density not decrease as space expands, as the density of everything else does? This question points to something deep about the nature of dark energy, something that distinguishes it from all other forms of matter and energy that we have encountered. If dark energy is indeed the energy of the vacuum, the energy of empty space itself, then perhaps its constant density makes sense. As space expands, we get more space, but each unit of space carries the same energy density as before, so the total energy increases as space expands. This is unlike matter or radiation, where the total amount is conserved even as space expands and becomes diluted. This fundamental difference between dark energy and other forms of energy might be the key to understanding its true nature. The quantum field theory framework, which underlies modern particle physics, suggests that every field in the universe has a ground state, a minimum energy state. Even when a field is in its ground state, even when there are no particles of that field present, the field still carries energy. This is called zero-point energy, or vacuum energy. The vacuum energy of all the quantum fields in the universe added together could plausibly be what we observe as dark energy. However, when physicists calculate what the vacuum energy should be based on quantum mechanics, they get a number that is vastly larger than what observations suggest it should be. This is the cosmological constant problem, one of the greatest unsolved mysteries in physics. The discrepancy is so large that it has been described as the worst prediction ever made by physics. Despite this puzzling discrepancy, the evidence that dark energy exists and has the properties of a cosmological constant is compelling. This suggests that either our understanding of quantum field theory is incomplete, or there is some mechanism that suppresses the vacuum energy to a value much smaller than we would expect. Resolving this mystery might require new physics, new theories that go beyond our current understanding of quantum mechanics and gravity. In the silence between stars, in the vast cosmic voids where nothing seems to exist except for the faint glow of ancient light and the presence of dark matter and dark energy, the universe continues its eternal dance of expansion and evolution. Dark energy, this mysterious force that we detect only through its effects on galaxies and the large-scale structure of the cosmos, works silently and invisibly, reshaping the universe moment by moment, stretching space, carrying galaxies apart, determining the future of the cosmos. We have learned to observe its effects with precision, to measure them with instruments of incredible sensitivity, to incorporate them into our models and theories of cosmic evolution. And yet, the fundamental nature of dark energy remains elusive, mysterious, wonderful. It is a mystery that will likely occupy physicists and cosmologists for many years to come, a mystery that might require revolutionary new insights and theories to solve. Perhaps what is most remarkable about dark energy is not that we don't understand it, but that we have found such convincing evidence for its existence at all. A century ago, astronomers did not know that the universe was expanding. They did not know that galaxies existed beyond our own. They did not know that the universe had a beginning or that it had a history. In just 100 years, through careful observation, creative thinking, and the development of increasingly sophisticated instruments and theories, we have come to understand the universe on scales and to a level of detail that would have seemed impossible to previous generations. And in the process of gaining this understanding, we have discovered something utterly unexpected, something that challenges our deepest intuitions about the nature of reality. Dark energy is a humbling discovery. It tells us that the universe contains within it things we do not understand, forces we have not yet explained, mysteries that remain beyond the reach of current theories. It reminds us that for all our knowledge and all our progress, there remain deep unknowns, profound puzzles, significant gaps between what we know and what we do not yet know. And perhaps that is fitting. Perhaps the universe is infinite not just in space and time, but also in the depth of mysteries it contains and the wonders it holds in store for curious minds willing to contemplate and explore. The study of dark energy has profound implications not just for cosmology, but for fundamental physics as a whole. If dark energy is real, if it dominates the universe, then understanding its nature is essential to understanding the universe at its most fundamental level. The current standard model of particle physics, which describes the behavior of the elementary particles and their interactions, does not include dark energy. It is incomplete, inadequate to explain one of the most important features of the universe. This incompleteness points to the necessity of developing new theories, new frameworks that can encompass both the successes of the standard model on small scales and the phenomenon of dark energy on large scales. Some physicists have proposed that dark energy might be related to extra dimensions, to strings, to quantum entanglement across cosmic distances, or to other exotic phenomena not yet discovered or understood. Others have suggested that gravity itself might need to be modified on cosmic scales, that what we interpret as dark energy might actually be a breakdown or modification of Einstein's theory of general relativity at extremely low densities. Still others have proposed that dark energy might be something entirely new, something that requires fundamentally new physics and new theoretical frameworks to understand. Whatever dark energy ultimately turns out to be, its discovery and the evidence for its existence represent a major milestone in human understanding of the cosmos. We have learned that the universe is far stranger, far more complex and far more wonderful than we had previously imagined. We have learned that there are aspects of reality that we do not yet understand, forces that we have not yet explained, mysteries that challenge the boundaries of current knowledge. And in contemplating these mysteries, in seeking to understand dark energy and its role in the universe, we are engaged in one of the most profound and important endeavors of human civilization. The attempt to understand the world around us, to penetrate the mysteries of existence, to peer into the deepest nature of reality. This is work that will continue for many years, perhaps for many generations to come, and it is work that is essential to our understanding of who we are, where we come from, and what our place is in this vast and mysterious cosmos. The universe invites us to join in this great adventure of discovery, to ask questions, to seek understanding, to contemplate the profound mysteries that surround us. And as we do so, as we engage with these deep cosmic questions, we grow in understanding, in wisdom, and in our appreciation for the remarkable universe in which we live. The implications of dark energy for the ultimate fate and structure of the universe are something we must contemplate with both intellectual rigor and philosophical openness. In the far future, in epochs so distant that the very concept of time becomes almost abstract, the universe will be a place profoundly different from what it is today. Yet in the present, in the universe we inhabit, in the cosmic epoch in which conscious beings like ourselves have arisen, the universe remains rich with structure, complexity, and possibility. We live in a time when we can observe distant galaxies, measure cosmic distances, contemplate the nature of space and time, and wonder about the forces that shape our cosmos. This is a privileged moment in cosmic history, a golden age of astronomy and cosmology, a time when the universe is still revealing its secrets to us. And we are the fortunate ones who live in this epoch, who have the knowledge and the technology to probe the cosmos and understand dark energy's role in its evolution. This knowledge comes with both the responsibility and the privilege of contemplating cosmic mysteries and seeking truth about the nature of reality.